Hello everyone, welcome to another lecture of CS 110 at Laurel Ridge Community College and VCCS. Today we are going to talk about Chapter 8, Abstract Data Types and Subprograms. Let me go ahead and share my screen. So welcome to Chapter 8, where we focus on abstract data types and subprograms. In this chapter, we'll explore how we can organize data and operations in a way that hides unnecessary details and makes program easier to build, maintain, and reason about. We'll look at different data structures such as lists, stacks, queues, trees, and graphs, and discuss how each helps us model different types of computational problems. We'll also see how subprograms, functions, and procedures allow us to break programs into smaller, reusable pieces. By the end of this chapter, you'll understand not only what these structures are, but also how they behave and what problems they solve. In this chapter, we'll start by distinguishing between two major ways to visualize container structures: array-based visualization and linked visualizations. Then we clarify differences between array lists and lists, which are often confused but serve different purposes. We'll also compare unsorted lists with sorted lists and see how this affects operations like searching or inserting. Finally, we examine stacks and queues, two fundamental abstract data types, and learn how to use their behavior, how they differ, even though both store collections of items. The second half of goals focus on tree-based structures. We'll distinguish between a general binary tree and a binary search tree and learn how to draw a BST built by inserting items one at a time. From there, we'll explore the difference between the trees and graphs, which model even more general relationships. Finally, we shift into subprograms, learning how parameters work and how values versus references parameters influence data flow inside functions. These core ideas are essential for structuring programs in any language. An abstract data type, or ADT, allows us to specify what a data structure does without specifying how it's implemented. The separation is crucial because it helps us manage complexity when we focus on properties and operations rather than low-level details. We can change implementations later without breaking the rest of the program. Think of an ADT like a contract. It guarantees certain behaviors, but it does not reveal the inner workings. This makes ADTs one of the most powerful tools in computer science. Three views of data: application label. At the application or user level, we think about data in terms of how it solves a problem. This view doesn't worry about how data is stored or implemented. It only focuses on what the data represents and what actions can be performed. For example, if we think about a playlist in a music app, the application level concerns itself with operations like next song, add song, or remove song. The underlying structure, whether array, linked list, or something else, is irrelevant to the user. Three views of the data. The first one is logical label. The logical or abstract label describes data in terms of its overall structure and behavior, but without specifying implementation. This is where we define ADTs. For example, a stack is a structure that allows push and pop operations and follows last in, first out behavior. The logical label doesn't care whether the stack uses an array or linked nodes. It only cares that the two fundamental operations exist and behave correctly. Implementation level is where we finally decide how the data is stored and how the operations are coded. Here, the abstract ideas turn into actual data, fields, and methods. For instance, a list might be implemented using contiguous array memory or using linked nodes connected by pointers. Each implementation has a trade-offs in speed, memory, and complexity. Get back to the slide. So it has trade-offs in speed, memory, and complexity, and each and programmers can choose based on problems that they are solving. Use of data again and composite data types. Composite data is a data type in which name is given to a collection of data values. So it bundles multiple pieces of data under one name. For example, a student record that contains a name, ID, number, GPA is a composite data type. Data structures such as arrays, linked lists, trees are implementation of these composite data types. When an object's main purpose is to simply hold and manipulate other objects, we call it a container. Container provides data structured ways to organize and access groups of data. Logical implementation. Two logical implementations of containers are array-based implementation and linked-based implementation. At a logical level, these are the two primary ways containers can be implemented. The first one, the array-based one, items are stored contiguously, allowing quick access by index, but it makes insertions more expensive. Second one is link-based. Items are scattered in memory, but each one points to the next. It makes insertions more flexible, but indexing slower. A good way to imagine a linked structure is a treasure hunt where each clue points to the next. So now we are going to move into a couple of important ideas that are very useful in interview preparations and for any tech jobs. This might be the basic principles that come in very handy while trying to do uh, while trying to write an algorithm for a problem that's given to you. So the first one is a stacks. A stack is an abstract data type that restricts access to just one end of the container. It follows the LIFO principle, last in, first out. You insert items using push operation and remove using pop. Everyday example of stacks include a stack of plates, your web browser history, or an undo feature in a text editor. In all these cases, the most recently added items is the first one to be removed. So here is a demonstration of an algorithm for stack operation. Working with physical objects such as cups or cars, you can visualize how pushing and popping would work in an algorithm. That's illustrated. And how pushing and popping would change the stack's state over time can be visualized here. Each push adds to the top and each pop removes from the top. This simple behavior makes stacks extremely powerful tools behind the scenes in programming, including expression evaluation and function call management. So basically, when you're looking at the two while loops, we see the first while loop is takes in more data as a parameter, and then it reads value and pushes into the stack on top of the stack. And the second while loop is while it's not empty, while stack is still has some value, it would pop the very first value from the stack and write the value as an output. So let's move on to queues. A queue is another fundamental ADT, but unlike a stack, it follows a FIFO, first in, first out items at enter at one end and leave from the other end. You might see different naming conventions like enqueue or insert and dequeue or remove, but the logic is same. Everyday queues include waiting lines, printer job lists, and processes scheduled by an operating system. The item that has been waiting the longest gets processed next. Here is an illustration of similar algorithm for queues, and like with stacks, using physical objects can help you visualize enqueuing adds items to the back while dequeuing removing from the front. And this ordering is what makes it ideal for scheduling tasks or handling events in a fair and predictable way. So in the first while loop, we see it reads a value and enqueues it to the queue. And the second while loop shows that until the queue is empty, you keep on dequeuing and write a value. Let's move on to the next one, which is a list. A list is the most flexible and commonly used data types. You can think of a list as simply a container holding sequence of items. On this slide, we focus on the core logical operations that any list should support. This include adding an item which inserts a new value into the list, removing an item which deletes a value, getting the next item which lets you walk through the list, and checking whether more items remain. What's important is that these operations are defined at the logical level, meaning they don't depend on whether the list is implemented with an array or linked structure. This abstraction keeps algorithms simple and reusable. Now, array-based implementation. Here we see an unsorted list of integers stored using an array. And in an array-based implementation, all elements are placed in contiguous memory. This allows very fast access by index, which is one of the key advantages of the arrays. However, operations like insertion or deletion can require shifting elements, which may be time-consuming depending on the list size. Unsorted lists are simple to maintain because new items can be placed at the end without worrying about order, but searching becomes slower. This layout gives us a clear visual of how array-based lists maintain structure. Linked implementation. Okay, let me get back to the slide again. Okay. Here we see an unsorted linked list. Unlike arrays, linked lists do not store their next elements in one continuous block of memory. Instead, each item links to the next through a pointer. This design allows insertions and deletions to occur efficiently, especially near the front, because you only need to adjust links rather than shifting many items. However, linked lists do not support quick random access. To get to an item, you must follow the chain from the beginning. This slide highlights how structure changes the trade-offs we face when choosing between implementations. Here's an algorithm for creating and printing a list. The question asked which implementation is intentional. The algorithm shown works regardless of whether the list is an array-based or linked. This is the power of abstracted data types. Algorithms written at the logical level don't care about underlying storage. Whether The items are in contiguous memory or linked nodes. The list's abstract operations hide those details, allowing the same logic to apply anywhere. To elaborate on the algorithm, the first while loop takes in data and reads the value, inserts it into the list. Then we reset it. Then we are displaying the list items in the list in the second while loop. We are iterating over the list items and writing them one at a time. Logical level. Here, the emphasis is on how algorithms operate at the logical level of abstraction. When we write algorithms using stacks, queues, or lists, we rarely think about how operations like push, pop, or insert are implemented. The logical level guarantees that these operations behave consistently. Even if the underlying internal representation changes, this separation frees programmers to design algorithms without needing to revisit or rewrite them when implementations evolve. It's a key principle in modular software development. Trees. Here we introduce an idea that structures like lists, stacks, and queues are all linear. They model a single, simple relationship between items. However, many real-world scenarios require modeling more complex relationships. That's where trees come in. Trees allow branching structures, representing hierarchical or multi-level relationships. Examples include organizational charts, file directory structures, and decision trees. When a problem involves multiple paths or nested relationships, linear structures aren't enough, and trees become essential tools. Binary tree. Binary tree is a special kind of linked structure with a single starting node called the root. Each node can have up to two child nodes, traditionally called left and right children. A key property is that there is exactly one unique path from the root to any other node in the tree. Binary trees serve as the foundation for many advanced data structures, including binary search trees, heaps, and expression trees. Their branching shape makes them suitable for organizing data that naturally forms hierarchies. This slide shows several kinds of nodes within a binary tree. The root node, internal nodes with different child configurations, the leaf nodes that have no children. It also asks you to identify unique path to various nodes, such as those containing 5, 9, or 7, highlighting that a binary tree structure determines how you navigate it. These paths are crucial when performing operations like search, insert, or delete. Understanding how nodes connect lays groundwork for mastering more specialized trees. I suggest that you pause your video and let the idea in this slide sink in. Moving on, binary search tree. A binary search tree or BST builds upon structure of binary tree but adds an important rule governing the values within the nodes. For any given node, all values in its left subtree must be less than the node's own value, and all the values in its right subtree must be greater. This semantic property creates an ordered structure allowing for efficient searching that can eliminate half of the remaining nodes at each comparison. BST provide a powerful combination of structured shape and logical ordering. I'll suggest that you pause the slide here and let the idea sink in from this binary search tree. Here is an illustration of binary search tree that shows how each node acts as the root of its own subtree. The left child represents all smaller values, right child represents the larger values. By thinking the tree recursively, each subtree being its own BST, we can design elegant algorithms for inserting, deleting, and searching. This recursive nature is one reason BSTs are commonly taught early in computer science. They demonstrate clean logical patterns that apply broadly across data structures. Binary search tree algorithm. Again, I'll suggest that you pause the video and let the idea sink in here and learn it in your own terms. So here we can visually reinforce the idea and the ordering rule. We can see the if-else statements and how is there function takes in tree and item as parameters and processes the information received within its code block. Every value in the left subtree is smaller and every value in the right subtree is larger. So even though it may look simple, it shows a powerful idea. Each comparison determines which direction the subtree, the search or insertion should go. And the operations can ignore one half and just look at the remaining other half. And it makes the search really fast when someone is looking for an item within such data structure. Understanding this structure prepares us for efficiently inserting and locating values. So elaborating on this algorithm, you can see that if first if checks if the tree is null and it will return false and basically terminate the code. And else part of it goes in and checks if the item is equal to tree, then you return true. If it's not equal to tree, and if the item is less than the info of the tree, then you check if it has a left node. If it doesn't have left node, it checks if it has a right node. And every time recursively, you're passing in and calling the function from within the code. Let's move on to the next slide. Again, I would say you pause the video and let the idea sink in here. This slide asks us to trace the nodes visited when searching for values like 18, 8, 5, 4, 9, and 15 from the binary search tree. Since the binary search tree obeys left is smaller, right is larger rule, searching becomes sequence of comparisons that guide us down the unique path. For each value, we start at the root and move left or right based on the relationship. This slide emphasizes the efficiency of BSD search. Instead of scanning the entire structure, we follow a direct route towards the target. It's a perfect example of how structure improves algorithm performance. Here is another slide for binary search tree, elaborating on the same algorithm we discussed earlier. This idea reinforces the ordering constraints. The takeaway is that the BST behavior depends entirely on maintaining the shape of the property of the binary tree and the semantic property of the ordered values. These rules make it possible to define clean recursive algorithm for insertion, searching, and traversal. With these foundations, we are ready to build actual BSTs and apply them to real-world data problems. So building a binary search tree, we see a binary search tree constructed from a series of string values. Even though strings are in numbers, they follow alphabetical ordering, which works perfectly for BST insertion. As each item is added, we compare it with existing nodes to determine whether it belongs in the left or the right subtree. This visual example demonstrates how the BST grows organically. Each insertion depends only on comparisons, and the final structure reflects the order of insertion. It highlights how flexible BSTs are regardless of the data type. Here is another illustration that shows how insertion would work in a tree. I suggest that you pause video here and let the algorithm sink in. Basically, we see how insertion happens step by step, and that will help you visualize how the tree emerges and clarify the logic and recursive nature of the algorithm. So each new string moves left or right until it finds an empty spot. This reinforces that BSC's final shape is not predetermined. It depends on the insertion order. Understanding this helps us prepare for discussions about balanced versus unbalanced trees. Here, we see that building a binary search tree is really this straightforward. The slide shows us that recursion is a powerful tool. It's a powerful tool for tree algorithms. Each subtree behaves like miniature tree with the same rules, so recursive insertion elegantly handles all cases. So it's a good example of mastering recursion and how it can help you express complex operations in simple, intuitive code. Particularly in the algorithm, we see that recursive call R1 and recursive call R2 are being made to the left and right of that tree until the tree is not null, and that's how the tree gets printed. Okay, we'll move on to the next topic of graphs. Graphs model relationships in more general way than trees. A graph consists of a set of vertices and a set of edges that link them. Some graphs are undirected, meaning the edges have no direction, while others are directed, meaning each edge goes from one vertex to another specific vertex. The graph can represent relationships like road maps, social networks, airline routes, or web links. They are incredibly flexible, making them essential in many computing applications. Here in this slide, we see examples of graphs. This visual illustrate how different graph shapes can represent different relationship patterns. We see some cycles, we see some branching, we see some linked nodes, and some that are not linked at all with any other nodes. The goal is to develop an intuition about how graphs can model a wide variety of structures. No matter the layout, the key idea is that graphs are defined by connections, not by strict hierarchical rules like trees. Here's another example. This additional example reinforces the idea that graphs can take many forms. They may be dense with many edges or sparse with only few. They might contain cycles or be acyclic. These different configurations affect how graph algorithms behave. Seeing multiple diagrams helps us visualize the many problems types that graphs can represent, from communication networks to dependency systems. In this particular graph, we see that the vertices are cities and edges are the direct flight to those cities. Here is yet another example of graphs, and it continues to showcase another kind of structure. The purpose is to help you recognize that graphs are universal tools for modeling relationships. Whether connections are simple or complex, directed or undirected, graphs lets us capture how things relate to one another without imposing necessary structure. These images set the stage for the searching algorithms we'll study next, like depth first and breadth first search. Here we see computer science 1 to computer science 2 being a prerequisite of, and then computer organization, and then how calculus 1, 2 is a prerequisite of discrete mathematics, etc. Vertices are courses and edges are prerequisites in this graph. Moving on to graph algorithms and a depth-first search. Here this slide introduces one of the most important algorithms used on graphs, the depth-first search or DFS. The idea is to find a path from starting vertex to an ending vertex by exploring as deeply as possible along each branch before backtracking. You begin at the start vertex, choose one of its neighbors, and continue moving forwards until you reach a dead end. Only then you return to earlier vertices and explore alternate paths. DFS uses a stack, either explicitly or implicitly, to keep track of the path. This method is especially useful for problems like maze solving, cycle detection, and exploring connected components in graph. Here is a graph algorithm example for depth-first search. It's a depth-first search algorithm example. So here's this visual example helps you understand how the search proceeds. The diagram illustrates step by step as algorithm dives deep into one branch before moving on to others. And stay with me, you may pause the video here and try to understand this algorithm line by line, as it has a lot more complexity than it looks like. It simply explores systematically. The algorithm's priority is depth, not minimal distance or minimizing stops. The example given here solidifies how DFS behaves and why it's useful in scenarios where full exploration is needed. And I would also suggest you to look up more resources such as articles or videos on this topic, as there are a lot of detailed videos that explain this, maybe in a 20-minute or 30-minute or an hour video sometimes. So it's a topic that you should explore if you're looking for to get a career in tech industry. Okay. Can we get from Austin to Washington using a stack? We apply a depth-first search to real-world themed example, finding a route from Austin to Washington. Diagram shows how the algorithm uses a stack to store routes during the search. Each time we extend the path, we push new city onto the stack. When we reach a dead end, we pop off the most recent city and backtrack. This demonstrates exactly how DFS works under the hood. The airline route framing makes the algorithm feel intuitive, almost like tracing possible travel paths on a map. Now, here is another visual that explains the same idea in a unique manner. This is the depth-first search in action, tracing the actual order in which cities are explored. By following the arrows, we see how algorithm may take a long and a winding path before eventually hitting the destination. This reinforces that DFS doesn't guarantee the shortest route. Its priority is to explore deeply, not efficiently minimizing the stops. This example helps you visualize how DFS behaves in real networks and why structure, not distance, determines the search order. Moving on to the next idea, which is breadth-first search, the fewest stops problem. After exploring DFS, we shift to a different question. What if we want to get from city X to Y using fewest airline stops. This is where breadth first search or BFS becomes the ideal solution. Unlike DFS, BFX examines all vertices adjacent to the start vertex first, then all vertices one level deeper, and so on. BFS uses a queue instead of a stack because we process older entries before newer ones. This level by level exploration ensures that when we first reach a destination, we have found the shortest path in terms of the number of edges. BFS is widely used in networking, routing, and shortest path scenarios. Here is a visual walkthrough of a BFS process. I would suggest that you pause your slide and let the algorithm sink in and notice the queue part of the algorithm and the DQ part of it, just like we had stack part of the algorithm in the DFS search. So BFS builds paths in increasing order of length as it examines all nearby nodes first and expands outward. Each layer of this graph is explored before moving on to the next. This guarantees that when we reach the destination, it's reached within minimum number of steps. The diagram makes it clear why using DQ and while using a queue is essential for maintaining the correct processing order. So once we apply BFS to the same travel problem from earlier, finding the fewest stops from Austin to Washington, the diagram shows Q holding each route as the algorithm searches outward from starting city. Because BFS expands by distance layers, the first time we reach Washington, we know it's the shortest possible route in terms of the stops. This practical example helps connect with BFS with the real-world optimization problems like airline routing, social network degrees, and communication paths, etc. So again, you may pause your video and let the idea sink in here. Here we see a complete breadth-first search path from Austin to Washington. The diagram highlights how BFS systematically explores nearest neighbors, then the next level, and so on. The first route clearly demonstrates how BFS avoids unnecessary wandering and instead moves outward efficiently until it reaches the destination. Seeing the method applied step by step gives a strong visual understanding of how BFS guarantees fewest number of stops in a route finding problem. Again, this is a quick overview of BFS and DFS. I'll suggest that you look up the idea and understand it through a lot of the examples that are published by many great authors on the internet. I'll complete the video part 1 for now, and I'll see you in the part 2 of this video real soon. Okay.